Okay, good morning. For today we are going to talk about manifolds and surfaces. The concept of a manifold is a very general concept, and here is the more intuitive version of that formal concept I can find, or I decide to show to you. Manifold is a set of points in which is locally like an n-dimensional space. So what does this mean? Imagine, use your imagination please. Imagine that you are in somewhere on the space and you look around you. If you need to describe n coordinates or n data, the amount of n data to describe the point you are looking at that around you, then we say you are in the n-dimensional space. For example, here in the Earth, it's natural for us to describe points with three spatial coordinates, yeah, like height, length, yeah, x, y, and z. You remember from your courses, of course, yeah. But we can think we are living in a universe of 4 dimensions. If you think in the fourth dimension to be the time dimension, and we can think that we live in a 5-dimensional universe. If you imagine, for example, that you need to define, you can't use the coordinates, three spatial coordinates, the time coordinate, and for example the kinetic energy coordinate. Then you have 5 data to describe one point. In this sense, we are talking about an space is n-dimensional, right? Of course, we need to go step by step at this concept, and for this we will see at what is a manifold of dimension 1. A manifold of dimension 1 is like a curve. A curve, it locally looks like a straight line. What is straight line? The tangent line, as in this picture. If you are an ant and you are moving along the curve, then you have the velocity is always tangential to the curve, and if you imagine stand up in that point of the curve, then you will see everything is plane. Yeah, you can imagine. Here I have 2 more examples of what I'm saying. This is called tangent bundle. The tangent bundle is, here is the curve, and at each point on the curve we imagine how does it looks like. Yeah, at this point you look your universe like this straight line. Yeah, you see. Yeah, you see like a straight line. Yeah. In formal terms, in mathematical terms, what does it mean to see a neighborhood or neighborhood like a 1-dimensional space is the following. If you are in the plane, let me come back. You are in the plane, 2-dimensional plane, but just imagine you are living inside the curve. How to describe points inside the curve? The idea, in accordance to my definition before of what means dimension about data, the amount of data used to talk about one point, it would be necessary just one parameter to describe points in the curve, and that's why we have a parametric form to describe. For example, the circle, this is the Cartesian equation, as you remember, and here we have the parametric form. The parametric form is describing the 2 coordinates x and y just depending on one variable, the variable t. So in that sense, formally is what we say, we just need to describe the points inside the circle. We just need one parameter. Yeah, you just need one variable. Now we have the manifolds of dimension 2. Manifolds of dimension 2 are surfaces. The surfaces are, for example, spheres, torus, the surface of a film of soap, hapenoids, yeah, and looks locally like a plane. The plane needs 2 coordinates to be described, yeah. So formally, a surface is a set of points in the space which looks like plane at every point. So this means here we are in the surface, and locally we see just a part of the plane, the tangent plane. It's the same situation like here, we are living here in the Earth, for example. We know that the Earth globally is curved, but locally always we see the floor plane. You see? Well, and in the of course, the Earth is a three-dimensional space, but inside the Earth, the surface of the Earth, it is possible just to talk about pointing inputs on the Earth just with two variables. For example, use this angle and this another angle to describe points inside the Earth, the surface of the sphere. Yeah, why we do not need this coordinate? Because the surface is always the same radius. Okay, here we are some other examples of surfaces, more examples here, and here we have non-orientable surfaces, which is a little bit more weird. There is, if you turn around this universe, then you will return to your starting point in a different way. Okay, and at last we have these minimal surfaces. This is like molecules in DNA and from soldiers. This is too much interesting. Minimal in the sense they minimize area. Yeah, here is another example right now. And in the general manifold we have this situation. Of course, the intuitive approximation is like as I showed recently. Okay, this is the all change. What is the real shape of our universe? Thanks too much. Have you any questions, please? Which points do you want I become more clear for you?
Well, why these manifolds are useful?
Okay, the manifold, the study of manifold, that's a great question. The study of manifold starts with this question. We need to understand what is the real shape of cosmos, of our universe in which we are living on. In the principles of the humankind, we think that our universe was just Earth. So we thought that the universe was plane. But with the histories what's going on, we realize that that's not true every time. Yeah. So the defining manifolds allow us to increase our understanding of, for example, this kind of situation. Who doesn't know the universe doesn't have this shape? For example, we could be living right here, and the universe could be in this way. So the object of the study of the differential geometry in mathematics is, roughly speaking, to trying to understand our universe. Starting from the point of local observation, we just have to make local observations, but we can't to see the universe in a global way. So it is necessary to develop a theory allowing us to go from local facts to global facts. That is the reason why we need to define manifolds in pure mathematics.
I have a question. When you describe a surface in that case, when you have a plane and next to that another plane and next to that another plane, what happened in the points where the planes are together? There are problems there in mathematician words to describe that surface or that points in the...
Let me see, you're referring maybe to this slide?
No, the slide where you was, for example, before, or in that case.
Here?
No, there. You have the catchnoid, and,
yeah.
I see a lot of little planes in that case.
Eventually the planes crossed.
Exactly. What
No.
happened in that points where they crossed?
No. We are just interested in how the universe, how the surface looks locally, near to the point. The word near is in the same sense as we learn in our courses of differential calculus. It's infinitesimal thinking. Yeah, you see, we don't care about what happens so far from the point when the points intersect. So we never think on this case with the planes cross. We only are interested in the near to the point. Yeah. Thank you so much.